How long will the sun survive? Chapter 1. The 10 billion year candle. If you could hold the sun in your hands, ignoring the minor inconvenience of instant vaporization, you would be holding a story 10 billion years in the making. It is a candle the size of a god, burning with a flame that began before humanity dreamed the first myths, and it is a candle with a predictable end. The question, how long will the sun survive, isn't just an astronomical curiosity. It's a clock that beats through all our histories and futures. To answer it is to lay out a calendar for the cosmos we call home. Today, our star is middle-aged, about 4.6 billion years have passed since a cold cloud of hydrogen and dust in a spiral arm of the Milky Way collapsed under its own gravity, spun faster, and ignited at the core. In that collapse, nuclear fire began. 4 protons pressed into one helium nucleus. A whisper of mass lost to a shout of energy, E equals mc squared, made manifest as light and heat. The sun has been converting mass to brilliance at a rate of roughly 4 million tons per second. And yet, even at that staggering pace, it has fuel for ages. It is a careful spender, not a pyromaniac. To know how long the sun will survive, we must first understand what survival means for a star. Stars live in phases, the way forests do. There's the stable summer of youth, the long golden afternoon, and then a brief, spectacular autumn. Survival can mean stability, or simply continued existence in any form. By one measure, the sun has about 5 billion more years of steady, life-supporting light before it exhausts the hydrogen at its center and leaves the comfortable plateau of its current life. By another measure, it will persist, changed, dim, and enduring as a white dwarf for trillions upon trillions of years, outliving every sea and city that ever rose under its light. The word survive needs a frame, but let's back up. The sun is a G-type main sequence star, one solar mass, a touch on the yellow side of white to our eyes. Its energy comes from the proton-proton chain, a series of reactions that build helium from hydrogen in the core, where the pressure and temperature are high enough to make protons, which repel each other electrically, tunnel through that repulsion and fuse. The core is about 15 million Kelvin. Photons born there take thousands to hundreds of thousands of years to random walk outward through dense plasma before breaking free at the surface as sunlight. What we feel on our skin at noon began its journey long before Rome fell, before mammals took their modern shapes, before any human language carved the word sun into air. This is the long, placid phase of a star's life. The main sequence, it's the era when hydrogen burns at the center and the star is in hydrostatic equilibrium, the inward crush of gravity balanced by the outward push of radiation and hot gas. For a star like ours, that equilibrium lasts on the order of 10 billion years total. The precise number isn't carved in stone. It depends on the sun's exact composition, the details of energy transport inside it, and how faithfully the nuclear reaction rates we measure in laboratories mirror the star's caged inferno. But the broad answer is robust. We are halfway through. If that answer sounds reassuring, good, it is. But the second half of a star's main sequence life is not a carbon copy of the first. As hydrogen fuses into helium, the core's mean molecular weight increases and the core slowly contracts under gravity to maintain pressure support, heating up and accelerating fusion. The sun is brightening about 1% every 100 million years. 10 million centuries from now, our descendants, if they still call Earth home, will see a slightly harsher sun, a subtle shift that ecosystems will feel long before any person tabulates it. Multiply that trend across eons, and the number becomes civilization-sized. This brightening is why the question, "How long will the sun survive?" has a sub-question with a tighter deadline. How long will Earth remain comfortably habitable under a sun that keeps turning up the dial? Different climate models disagree on the fine print, but they rhyme in their verdict. In about 1 billion years, the sun's luminosity will be roughly 10% higher than today. By somewhere around 1 to 1.5 billion years hence, Earth risks entering a moist greenhouse state. Oceans evaporate faster than the planet can cool. Water vapor climbs to the high atmosphere, where ultraviolet light splits it, and hydrogen bleeds into space. On that time scale, the seas retreat. Coastlines become myths. The azure marble goes the way of Venus, a desert under a white sky. So, the sun's main sequence survival continues serenely, but our survival under it confronts a nearer horizon. That horizon is vast to human minds, longer than the time from the first multicellular life to today, but it's not the 10 billion that casual comfort imagines. 1 billion years is a generous bounty of time for an intelligent species, enough to boot civilization 1,000 times over if it chooses, enough to seed many other worlds with forests and stories, but as a planetary calendar, it is a due date, stamped in the slow physics of a brightening star. Now, what happens when the main sequence ends? Eventually, maybe in 5 to 6 billion years, the sun will have exhausted most of the hydrogen in its core. Hydrogen remains in the outer layers, but the heart becomes a sphere of helium ash. With no more central fusion to prop it up, the core contracts and heats. In response, the shell of hydrogen just above the core ignites. Hydrogen shell burning, the sun swells. The photosphere, its visible surface, moves outward to volumes where gravity is weaker and the gas cooler. The star reddens and brightens and grows into what we call a red giant. When you read that phrase, don't picture a gentle enlargement, picture a transformation. The sun's radius will inflate first gradually, then dramatically. Mercury will be swallowed, Venus too. And Earth? Its fate is a coin on edge. The sun will lose mass through a more vigorous solar wind as it ascends the red giant branch. That mass loss causes the orbits of the remaining planets to expand. Meanwhile, the sun's radius grows toward and perhaps past Earth's current orbital distance. Will our planet spiral outward faster than the sun balloons, evading the fiery lip? Or will tidal interactions and drag in the star's tenuous outer atmosphere pull Earth inward to a spectacular demise? The truth is murky at the margins. Most models suggest the Earth will be engulfed, but some show a narrow, miraculous escape where the planet is roasted to sterility but not swallowed. Whatever the precise geometry, life here will be long gone by then. These are questions of archaeology, not rescue. After climbing the red giant branch, the sun's core will become hot and dense enough, about 100 million Kelvin, for helium fusion to begin. Because the core is, by then, supported partly by electron degeneracy pressure, that ignition is not a smooth dawn. It's a helium flash, a runaway onset that releases a vast amount of energy in moments, but trapped within the star, unseen by distant worlds. The sun then settles into a new equilibrium for a short, brilliant chapter, fusing helium into carbon and oxygen in its core. While hydrogen continues to burn in a shell, This is a stable horizontal branch or red clump phase for roughly 100 million years, a coffee break compared to the main sequence. When the helium runs out, the dance repeats. The core, now composed mostly of carbon and oxygen, contracts again. The outer layers swell anew into the asymptotic giant branch, AGB phase, with alternating shells of hydrogen and helium fusion, punctuated by thermal pulses that swell and shrink the star in cycles. In these throes, the sun will dust the solar system with some of the heavy elements forged in its interior carbon that future planets, moons, or comets could one day fold into chemistry and perhaps into life. This is the sun's leaf fall season, and it is gorgeous. Eventually, the sun will shrug its outer layers entirely, not in a supernova. The sun is far too light for that, but as a luminous, delicate bubble called a planetary nebula. The exposed core, now a white dwarf about half the sun's current mass and roughly the size of Earth, will glow at first as hot as a faint star, then fade on billion-year, trillion-year, and longer time scales as it cools. It will not burn. It will not change its composition. It will simply radiate away stored heat, the final ember of a life lived entirely under gravity and electromagnetism. So, how long does the sun survive? Let's lay out the answer as if we were inscribing a timeline on the inner brass of an ancient astrolabe. Now to plus 1 billion years. The sun brightens by to 10%. Earth warms. Ice retreats further. Weather patterns shift. Life adapts, migrates, or fails. The cosmic background hum does not notice. Plus 1 to plus 1.5 billion years. Earth risks entering a moist greenhouse. Oceans shrink. Water vapor lofts high, gets split by sunlight, and hydrogen escapes to space. By the end of this era, oceans may be gone, or mere shadows of themselves. Complex life, if not already departed for other worlds or refuges, confronts an endgame. Plus 2 to plus 3 billion years. Runaway greenhouse dynamics likely complete Earth's transformation into a dry, hot world. The sun continues to brighten gently. The main sequence continues, plus 5 to plus 6 billion years. Core hydrogen exhausted, hydrogen shell burning begins. The sun swells into a red giant. Mercury and Venus are lost. Earth is almost certainly uninhabitable and likely engulfed. Shortly after, helium flash ignites core helium fusion. The sun settles into a new, temporary stability for to 100 million years. Following that, the sun enters the AGB phase with pronounced mass loss, beauty born of farewell, a planetary nebula. Afterward, the sun becomes a white dwarf, a carbon-oxygen cinder, crystalline at heart, cooling for time so long that language stumbles. Trillions of years and more, dimming toward black, though the universe itself may change its rules before the ember fades to absolute dark. If survival means operating as a star like the one we know, a stable, life-friendly engine in the sky, then the sun survives about 5 billion more years. If survival means persisting as an object, then the sun's remains endure longer than you can easily imagine, longer than present galaxies will retain their shapes, longer than the age of the universe so far, by factors so large that metaphor gives up. These are not guesses scribbled in the margins of astronomy. We have evidence. We read the sun's future in the Hertzsprung-Russell diagram, a star atlas drawn not on paper but in the sky itself, plotting brightness against color. We watch other sun-like stars at different ages, children blue, white, and fast, elders red and swollen, and put the sun along that track. We study globular clusters whose stars all form together, where the turn-off point from the main sequence reveals the age of the cluster and the lifetimes of its stars. And we build suns in miniature, stellar models that solve the equations for structure and energy transport from core to surface, tuned against helioseismology, acoustic ripples inside the sun that let us listen to its interior. The models and the observations agree in their broad strokes, the way a clock's hands agree with time. None of that means the future will unfold like stage directions. There are unknowns at the edges. How much mass will the sun shed exactly as a red giant? How strong will tidal interactions be with Earth if any of the sun's extended envelope brushes our orbit? How will magnetic fields braid and break during the final thermal pulses? These are details for the aficionados, the way a connoisseur might discuss the particular chemistry of a leaf's color in October. The season itself is not in doubt, but the sun's survival story isn't just about astrophysical grace notes. It's an invitation to think like a civilization. 1 billion years is incomprehensible to a creature whose heart beats 4,000 times in an hour of sprinting, whose day ends when the sun falls behind rooftops. And yet, we have been given the gift of this foresight. We know the stage on which we move is changing on a schedule measured not in decades or dynasties, but in geological pages. If any descendants of ours, biological or technological, carbon-based or silicon-sheathed, wish to keep oceans and rain and wild sunlight in their days, they will need to move outward, Mars first, perhaps terraformed and warmed by artificial greenhouse blankets, then the outer moons, whose buried oceans may one day see open skies. Later, much later, as the sun swells, humanity's heirs may take their biomes to the Kuiper Belt, building worlds from ice and patience. The sun's increasing brightness, a slow catastrophe for Earth, becomes a blessing to colder realms. Survival bends into migration, calendar becomes map, and then there is the longer dream. In the deep future, when the sun becomes a white dwarf, a diamond the size of a world with a warm heart, its gentle glow will be a hearth for anything that still cares, anything that remembers. One can imagine ring worlds or swarms of habitats sipping that dwindling heat, their cultures synchronized to centuries instead of days, as the universe cools. Or perhaps the story forks elsewhere, into other stars, other galaxies, other books. The sun's survival is not our prison. It is our first teacher in all matters of time. Ask, finally, what kind of feeling this knowledge should leave us with, and the answer is not fear. It is clarity. The sun is not capricious. It does not rage. It evolves. With each sunrise, we are given one more page of the long afternoon of the main sequence, one more chance to work, to learn, to decide who we will be when the afternoon leans toward evening. We are rich in hours and poorer by one every time the light slides down the side of a building. Our star teaches thrift without anxiety. Spend the day well. There are countless more, but not infinite. And so, to the question, how long will the sun survive, we answer in sentences and in scenes. In sentences, about 5 billion more years as the star we know, then a short red blaze of elderhood, then a quiet ember for ages beyond ages. In scenes, an ocean turning to mist like breath on glass, a sky whitening and emptying of clouds, a star pulsing red like a heartbeat, a frail halo blooming in space, a white spark left behind, patient as stone. If you step outside tonight and look up, you are not seeing a mystery. You are seeing a promise written in hydrogen and time. The sun will keep its word. It will light our tomorrows and the tomorrows of worlds not yet imagined. It will be there, reliable and relentless, until one day it becomes something else. And even then, it will not be gone. It will become a memory that still warms the dark. We have time, not forever, but time enough to be worthy of this light. Chapter 2. The Long Goodbye and the Map of Forever. There's a photograph taken by the Solar Dynamics Observatory of the sun in extreme ultraviolet. It looks like a coin made of lightning filaments like handwriting, bright knots that flare in magnetic storms, a surface that boils in granules the size of continents. Stare at it long enough, and you start to feel the contradiction that defines our star. Wildness contained. It is a roaring engine housed inside a near-perfect sphere, a storm whose rules are so strict that we can use them to keep time. That is why we're able to ask, without superstition, how long the sun will survive, and to answer not with a shrug, but with a calendar. This chapter is the map behind that calendar. It's the story of how we know and what the knowing suggests for Earth. For any species ambitious enough to plan beyond the next ice age, and for the sun itself as it transforms from the monarch of day into a quiet ember in the deep night of time. How we read a star. The sun looks simple because distance scrubs away detail, but it is layered like an onion, each layer governed by equations so consistent that they might as well be promises. Astronomers build what they call the standard solar model, a set of equations that describe hydrostatic balance, energy generation by nuclear fusion, energy transport by radiation and convection, and how composition changes as hydrogen becomes helium. A model is only as good as its tests. So we test it with 3 listening posts. First, we listen with helioseismology. The sun rings like a bell. Pressure waves, modes, bounce around inside it, their frequencies set by the temperature and density of each layer. By measuring tiny ripples on the surface minute Doppler shifts across the solar disk, we infer how sound travels inside the sundae. That sound speed profile is a CT scan of the star's interior. When the model and the sound agree, we trust the script enough to read ahead. They do. Second, we listen with neutrinos. Every time 4 protons fuse into helium, neutrinos are born ghost particles that hardly interact with matter at all. For decades, detectors buried in mines and under mountains counted fewer solar neutrinos than models predicted. That discrepancy, the solar neutrino problem, felt like a splinter in the mind. It turned out that neutrinos change identity mid-flight, oscillating between flavors. Once we accounted for that, the count and the model matched. The sun was not lying. Our detectors were misunderstanding. With that reconciliation, we gained confidence that our core temperature estimates were not fantasies. Third, we listened to the sky itself. Plot stars on the Hertzsprung-Russell diagram brightness against color, and they line up in bands that trace their lives. In globular clusters, where all stars formed at nearly the same time, the point at which stars peel off the main sequence tells us the cluster's age. Comparing stars slightly heavier and slightly lighter than the sun lets us bracket the sun's path. The sun is not unique, it is typical, and that typicality is a gift to prediction. These tools, together, let us tell the sun's future in broad strokes, a remaining main sequence lifetime of roughly 5 billion years. a red giant phase that swallows inner worlds, a helium-burning interlude, a final shedding of gas into a planetary nebula, a white dwarf relic cooling for astronomical eternities. Yet the "how long" hides a second question with human teeth. How long for us? The faint young sun and Earth's thermostat. Here's a paradox that calibrates our confidence. Early in Earth's history, the sun was dimmer, perhaps 25–30% less luminous than it is today. A naive calculation says Earth should have been a frozen marble for billions of years. It wasn't. We have fossils and rock chemistry testifying to liquid water and life. That mismatch between expectation and evidence is the faint young sun paradox. The solution is a thermostat older than continents, the carbonate-silicate cycle. Volcanoes exhale carbon dioxide. Rain pulls it down. Rivers carry it to oceans where it's locked in rocks. Tectonics buries and returns it. Warmer climates accelerate weathering and draw down CO2. Colder climates slow weathering and let CO2 accumulate. Over millions of years, that negative feedback keeps climate within survivable ranges, even as the sun turns the dimmer slowly upward. The thermostat is clever, but it isn't omnipotent. As the sun brightens another 10% over the next billion years, the thermostat will struggle to keep pace. Water vapor, a potent greenhouse gas, will climb higher, and once it reaches the stratosphere in large amounts, sunlight breaks it apart, hydrogen escapes, and Earth begins to desiccate. Geological feedbacks that once stabilized temperature now lock in dryness. The same chemistry that saved us from freezing eventually writes a different ending. The sun's survival isn't our problem, it's our abundance. Too much light is not a gentle excess. It is eviction, served slowly. This is the first horizon we truly feel. Not the red giant's drama, but a 1 to 1.5 billion year window in which Earth slides from ocean world to a parched planet that remembers rain the way we remember myth. On that time scale, civilizations have options. The options are grander than anything we currently attempt, but they do not require wizardry. They require continuity, engineering time, what we could do. The anthology of ideas to postpone or finesse Earth's overheating ranges from the surgical to the audacious. Some are unglamorous geoengineering patches, sunshades at the L1 Lagrange point, particles in the stratosphere to reflect a small fraction of sunlight, mirrors on long orbits that dim noon by a sliver. These are bandages. They buy time, not reprieves measured in eons. A 10% brightening is a mountain, and we would be sand shifting at the summit. The more architectural proposals rewrite orbits. You can, in principle, move Earth outward. The method is counterintuitive. Use gravity like a clutch. Herd a series of large asteroids onto carefully timed trajectories that steal a bit of energy from Jupiter and give it to Earth through gravitational flybys. Each pass is a whisper of a push. Over millions of years and many rocks, the whispers add up to an orbital migration. It's celestial billiards with a rule book written in conics and conservation of momentum. The risks are not subtle. You do not practice near misses with worlds. But physics doesn't forbid it, and time is on the side of careful planners. Another family of ideas wraps itself around the sun rather than Earth. Stellar engines. A Shkatov thruster, a hypothetical megastructure that acts as a giant mirror, could reflect a fraction of the sun's radiation asymmetrically, producing a minuscule net thrust that drifts the entire solar system over unimaginable time. That's not a fix for climate. It's a gentler, more cosmic ambition. The point of mentioning such machines isn't to sell blueprints. It's to emphasize the range of agency an ancient species might wield if it makes it through the eye of history and keeps adding knowledge to patience. Meanwhile, there is the simplest answer of all. Move, Mars, the asteroid belt, the moons of Jupiter and Saturn, the dwarf worlds in the Kuiper belt. These are cold now, but the slow brightening of the sun makes them less hostile. With each 100 million years, terracing a future across worlds is not surrender. It's flourishing that admits what the landlord has posted on the door. Red autumn, when the sun swells. Beyond our billion-year horizon lies the shape of the sun's late life, the part of the script you would not want to miss even if the theater were cold. When core hydrogen runs low, the sun's center contracts and heats. Hydrogen begins to fuse in a shell around a helium core. The outer layers, less tightly bound by gravity, expand and cool. The sun reddens. It will grow tens to hundreds of times its present radius. The photosphere, its visible edge, will drift toward where Earth's orbit is now. Two processes compete for Earth's fate. As the sun inflates, it loses mass in a stronger solar wind. Less mass means weaker gravity, which lets planetary orbits expand. But the sun's swollen outer atmosphere is extended and slow. If Earth finds itself plowing through this gas, drag and tides will sap orbital energy, lose more to drag than you gain from mass loss, and you spiral inward toward incineration. Gain more than you lose, and you drift outward to a scorched survival. Most calculations tip toward engulfment, but there's a sliver of parameter space where Earth makes it to the clifftop, burned dead yet unconsumed. It is the rare cliffhanger with no sequel worth watching. Even if Earth somehow dodges, life is gone by then. The action moves outward. Mars becomes temperate for a while, its air re-thickened by released volatiles. Europa and Enceladus open their ice today. Titan's smog thins into an orange spring. For a few 100 million years, the helium-burning interlude, after the red giant's steepest ascent, there's a second act of habitability in cold places. Imagine a civilization stringing cities across the Kuiper belt, then reading in the sky as the sun's halo turns copper and the light becomes wine-colored afternoon. Red giants pulse. They do so because thin shells of nuclear burning can't decide on a tempo. They heat, expand, cool, then reheat. These thermal pulses are not random. They are rhythmic quakes of a star's last great breath. With each pulse, the sun will shed more of its outer layers. Dust forms in that outflow, carbon dust, silicate dust lighting the red giant wind like fields of fireflies. That dust is not waste. It is feedstock for future planets, comets, and chemistry elsewhere. The sun's afterlife begins here in a drift of soot that will one day scent other skies. When the helium is gone, the core, now mostly carbon and oxygen, lacks the pressure and temperature to ignite new fusion. A one solar mass star cannot push further up the nuclear ladder. The sun becomes unstable in earnest, shrugging off its envelope entirely. The hot core is revealed. Ultraviolet light floods outward and ionizes the shed gas. A planetary nebula blooms. A shell, sometimes a ring, sometimes an hourglass or a butterfly, glowing for tens of thousands of years. The shapes that photographs show the cat's eyes and halos, the crisp rims owe much to magnetic fields and to unseen companions. Because the sun is most likely alone, we expect its nebula to be modest, an elliptical glow, beautiful still, if you are far enough away to see it whole. The white dwarf, a diamond in a velvet box. What's left is compact beyond intuition. A white dwarf about the size of Earth, but with half the sun's mass, a crush so intense that a teaspoon would outweigh mountains. The pressure that supports it is not the frantic motion of hot gas, but the quantum degeneracy of electrons, a kind of no two-in-one-seat rule enforced at cosmic scale. The surface gravity is brutal. If you could stand there, you cannot. You would weigh hundreds of thousands of times more than you do now. At first, the white dwarf is hot hundreds of thousands of degrees at the surface, millions inside, but it has no fuel left to burn. It radiates its heat away like a stove cooling in the dark. Over billions of years, it dims to red, then to black in colors we could only see with time-lapse measured in eons. Inside, the carbon and oxygen crystallize. Think of it as a diamond heart growing over epochs, an image both poetic and literally correct in spirit. The main clock for cooling is mundane. It's just how fast heat can leave a dense sphere. But there are surprises, phase changes that release latent heat, processes at the quantum edge that slow the descent. Some estimates of a white dwarf's cooling to invisibility wander into trillion-year and even quadrillion-year timescales. Those numbers stop behaving like numbers we use for planning. They become a kind of stillness. Around that white dwarf will be a changed solar system. Jupiter and Saturn will survive, moved outward, tyrants in a quieter court. Mars and the remaining rocky debris will be cinders, some flung away by the chaos of the red giant wind, some left to circle forever. We know something about such systems because we have found white dwarfs with polluted atmospheres, heavier elements like calcium and iron that shouldn't be there because gravity should have dragged them down. The contamination comes from tidally shredded asteroids and minor planets that wandered too close and were ground into disks and rain. Planetary systems endure, but their bones get ground and taste of iron. If anyone or anything lives there in shells, stations, or engineered worlds, they will live with a sky that never rises, only fades. Day and night will not exist. Only dimness will change, century by patient century. The sun will have become an object, not a star, and its survival will be measured not in fuel, but in heat left to lose. The neighborhood responds. The sun will not die alone. It is one bead in a galactic rosary. As it ages, so too will other stars. Red dwarfs, born with less mass and engines that sip instead of gulp, will outlast the sun by orders of magnitude. Some will still be burning when the sun's white dwarf is an old fossil. Massive stars, the blue-white sprinters, will have exploded long before. The Milky Way itself will have merged and rearranged, cities of stars crossing and blending. The Andromeda Galaxy will have long since woven itself into our fate. The large-scale ballet rearranges neighborhoods, stirs comet reservoirs, sends long, lazy hailstorms into inner systems. The sun's biography sits inside this wider epic. This is not trivia. The sun's future planetary nebula will glow against a changing backdrop. Its white dwarf will drift through a galaxy whose gravitational politics are rewriting the map. Occasionally, a passing star will tug on what remains of the Oort cloud, sending comets sunward to vaporize in a belated spectral rain. The point is not to keep count. The point is to feel scale. The sun's survival even as a dim cinder is long enough to watch the shape of the night change. Lessons folded into light. If you strip the dates off the timeline and read it as a fable, two lessons remain. First, stability is dynamic. The sun looks constant, but its constancy is produced by tension, gravity inward, pressure, and radiation outward, renewed every instant. The lesson translates cleanly into human life. Our cities, economies, and cultures are not frozen things. They are equilibria, maintained by flows of energy, of information, of trust. To imagine we can keep what we love without tending the flows is to misunderstand the sun, which never rests but never panics. Second, endings are not failures. The sun will end its main sequence life not with an explosion, but with transformation. It will give away mass to the dark. It will light a nebula that will seed future worlds. It will contract into a white dwarf that remembers heat. None of that is a glitch. It is the design. If we map that lesson onto our own arc, we might find a generosity of planning. Invest in institutions and knowledge that outlast specific forms. Plant trees in the Kuiper Belt you will never see. Build languages that can be read 1,000 years hence. Leave messages carved into engineering itself, standards, redundancies, thermostats that make it easier for descendants to inherit without starting from ash. The original question, how long will the sun survive, now reads like two questions stitched together. How long will it remain the sun we know? About 5 billion more years. How long will it persist as a thing in the universe? For trillions of years as a white dwarf cooling toward quiet, perhaps longer still if matter has tricks we haven't measured, perhaps shorter if protons are not forever. Those sentences are clinical. Let's translate them into scenes. Scene 1. A future Earth before the Exodus. High summer. The sun whiter than we remember. The air dry as paper. Forests tucked under domes in the mountains where rivers still remember their work. Children learning maps that include orbit change projects as casually as we teach bridges. Museums where a glass holds real seawater, a liquid that once covered whole continents. Scene 2. Mars at dawn. The sky the color of salmon, thicker now. A settlement spreads around the rim of an ancient crater. A canal glints not as historical era, but as present tense. The sun a touch brighter, the day a touch warmer. They plant birches that have been coaxed into liking thin air and red soil. Scene 3. The Kuiper Belt. A city of 100 million cold lights. The sun small, crisp, bright. From here it looks like a pearl you could thread. Forward, long sails sip pressure from light itself. Backward, the great dark. Scene 4. Red giant noon above Titan's lakes. The sun a bloated coin. The cold world steams in a slow ecstasy. Humans are not here, not necessarily, but something clever is, built by hands that borrowed our idea of hands. It floats on a caramel sea and watches a sky that has learned to be both orange and luminous. Scene 5. A planetary nebula, seen from far beyond Neptune's old haunt. A shell of gas like a cathedral window, delicate and precise, expanding so surely that you could set a clock by it if you had a few millennia to spare. In its center, a dot too bright for its size. The white dwarf we will one day call by a new name. Scene 6. A habitat drifting in the long after. The sun is no longer a direction, it is a hearth. Its spectrum has steeped to red. There are gardens and archives and rooms where the ceiling shows the milky, faint ring of what used to be the Kuiper Belt. Now a sculpture. None of these scenes are necessary. The universe owes us nothing, but they are all allowed by the physics written in the Sunday. That allowance is the quiet optimism of astronomy. The rules are strict, but inside them there is room enough for courage. The last page. It is tempting, at this point, to chase the end of everything. Will the white dwarf cool to a black dwarf in which atoms sit like sleepers in a crypt? Will protons decay after 10 to the 30-something years, turning even the bones of matter into neutrinos and light? Will the cosmological constant thin or thicken, stretching space until no neighbor can see another neighbor, every light isolated in privacy? Those are questions with answers not yet earned. They belong to physicists working at edges where experiment becomes ingenuity. The sun's story does not need those edges to be complete. It is already an epic with 3 acts: Genesis, sustenance, transfiguration. In the first act, a cloud collapses and a star lights, surrounded by leftover rock and gas that coagulate into planets. In the second, hydrogen turns into helium and the light is steady as a metronome for billions of years, while chemistry learns to write itself into cells and cells into thought. In the third, the balances tip. The star grows, sheds, settles. A nebula blooms and fades. A white dwarf cools through eras so long that language cannot keep up. Where are we now? We live in the middle of Act 2. The orchestra plays a theme repeated for 4.5 billion years. The tempo has quickened by barely 1%. That is the kind of change that invites complacency. Resist it, not because doom looms tomorrow, but because a species that can know this story is a species that can choose. If we are the only audience to which the sun can explain itself, then we have the duty to be a good one, to listen, to plan, to make use of the long afternoon without burning the furniture to keep warm. Step outside again. The sun is there, not because it must be, but because gravity and fusion and quantum rules have conspired to keep it there. It will keep its promises. 5 billion more years of ordinary miracle. A red fall glorious enough to be remembered by anything in the neighborhood that has eyes. Then a long winter lit from within. We often console ourselves by saying that nothing lasts forever. The sun suggests a revision. Almost nothing lasts forever. But some things last long enough to build meanings that feel like forever from the middle. The sun is one of them. If we do our part, if we learn to think in centuries without losing the day, in millennia without losing the child, then the sun's survival becomes a landscape, not a deadline. We will walk it as far as we can, and when we cannot walk further, we will have left paths, shelters, recipes, and songs for whatever comes next. And that is the answer. Illuminated by the thing that asks the question each morning when it climbs the horizon. The sun will survive as the sun we know for about 5 billion more years, and as a transformed remnant for ages that make the word age feel young. We will survive under it for as long as we are capable of making good maps from true light.